One really great application for vector valued functions that really ties together the calculus that we learned in the last section with our vector valued functions is projectile motion. So we're going to be shooting some sort of projectile, and the only thing we really have control over are the conditions that we give this projectile right at the second that we shoot the projectile. So our projectile may start at initial height h, and then that arrow represents our initial velocity, and then that velocity is usually applied at a specific angle theta with the horizontal. The other thing that we know at the beginning of this problem is that the only thing that is acting upon this projectile once we shoot it is acceleration. And acceleration is just a downward gravity acceleration. And depending on whether we're working in metric units or US customary units, we will use a different value for G. If we're in metric, we use negative 9.8 meters per second. If we're in US customary units, we use negative 32 feet per second. So I'm going to go through how exactly we derive the projectile motion vector valued function. It's good to know where all the values are coming from and where the formulas are coming from, but I won't ever ask you to recreate this derivation. So just sit tight and enjoy. Since the only thing we know at the beginning is acceleration, I'm going to start with that formula. Our acceleration is straight down, which is in the y direction. So as a vector, we can think of acceleration as 0i and then minus the g value for our j component. And the g is just a constant. I'm not going to put one particular value in yet because we want this to be able to apply to lots of different types of problems. Well, we learned in the last section, the beginning of this section, that acceleration is second derivative. So if we integrate both sides with respect to t, it will take us back to a velocity equation. The antiderivative of 0 with respect to t is just a constant. And then the antiderivative of a constant is that constant times t. So we've got a starting place, at least for like the structure of what our velocity function is going to look like. We do have some information about velocity at time 0. We know that it has a magnitude of v sub 0 at an angle of theta. We can take that information, take magnitude and direction, and actually write it as a vector. Remember, the way that you change from magnitude and direction into components is using sine and cosine. So as components, this is v sub 0 cosine theta I and v sub 0 sine theta j. And we got this using the information at the beginning of the problem. So if we take our vector and put 0 in for t, these two v of zeros should match. So I'm going to take mine and plug t equals 0 in, and I get c1i plus, well, negative g, no matter what value g has, when we multiply it by a t value of 0, it's going to zero out. So we just have c2j. And these two vectors are equal, which means their components must be equal. So c1 must equal v sub 0 cosine theta, and c2 must equal v sub 0 sine theta. So this leads us to a better formula for velocity that has no arbitrary constants in it. So now I go back to here and replace C1 and C2. So C1 was V sub 0 cosine theta. That is our I component. And then for our J component, we've got negative GT plus, now C2 is equal to V sub 0 sine theta. So if we knew what system we were working in, we could replace the G, and we could also replace initial velocity and sine and cosine theta if we had the specifics for the start of this problem. Now, we're going to do this whole entire process one more time because we're trying to get a position function. And if you do the antiderivative of velocity, it will take you back to position. So we'll calculate this antiderivative, and what we initially get for a position function, V sub 0 cosine theta, we're integrating this with respect to t, and since there are no t's in there, it's a constant. So our antiderivative is V sub 0 cosine theta t plus some arbitrary constant. Every time we do an indefinite integral, we will have an arbitrary constant. And then for our j component, we need to do the power rule on negative gt. So we get negative g over 2t squared. And just like before, v sub 0 sine theta is a constant. So its antiderivative is going to be v sub 0 sine theta t, and then plus n another arbitrary constant, c sub 2. Well, we know our initial position. It's always going to be the point 0, h, or as a vector, if we point at our initial position, this vector would have a format of 0i plus hj, which means if we plug 0 into our vector valued function, those should match up, and that's going to allow us to solve for C1, C sub 1, and C sub 2. So if we plug 0 in for t's, the only thing we have left is C1i plus C2j, which means for the second iteration of this whole process, C1 is 0 and C2 is h. And this leads us to a nice formula that we can use for projectile motion if we know what units we're using and our initial velocity, the angle, and our initial height. So I'm going to go back to my antiderivative and replace the C1 and the C2 values. And this will give us a nice formula that we can use for position of a projectile. So we've got V sub 0 cosine theta t, C1 was equal to 0, so we can just leave that off, plus negative g over 2t squared plus V sub 0 sine theta t, and then C2 was equal to h for our j component. So this is our magic projectile motion formula. It's also very common when we work out application problems to separate this vector valued function into parametric equations and just work with the x equation and the y equation individually, because they both tell us two completely different things about this projectile. X of t tells us what's going on horizontally as this projectile flies through the air. Y of t tells us what's going on vertically as this projectile flies through the air. So it's also common, you might see, let me give myself a little bit of space here. So it's also common for us to break these apart and work with them as parametric equations and say x of t is v sub 0 cosine theta t. That's the equation that tells us what's going on horizontally. And y of t is negative g over 2t squared plus v sub 0 sine theta t plus h. And that tells us what's happening to our projectile vertically. Some common questions that we are asked about projectile motion are maximum height and range. So maximum height is going to occur when y prime of t equals 0. So if you look back at our graph, you can probably just eyeball where the maximum height is. And what's special about that point is that we have a horizontal tangent line there. Since we're working with vector valued functions, we will have a horizontal tangent vector there. And remember, our velocity vector is our tangent vector, and velocity is first derivative. And height only refers to what's happening in the y direction. So we can find maximum height by solving where y prime of t equals 0. It's also very common for us to be asked to find range. And range is asking us how far horizontally did this projectile travel before it hits the ground. So the special thing about that spot is that it hits the ground when y of t equals 0. So if we know when it hits the ground, we can take that value and plug it into our x equation to find how much horizontal distance has been traveled in that time. So we solve y of t equals 0 for the range. So I've got two examples I want to show you. The first one, not really an application problem, just a practice with our vector valued function for projectile motion, but then I have another one that's a little bit more difficult and is an application problem. So for this first example, we've got a projectile that's fired from 2 meters above the ground with an initial velocity of 75 meters per second at an angle of 35 degrees with the horizontal. That is all the information we need to know in order to set up our vector valued function. So 2 meters above the ground, 75 meters per second, 35 degree angle. And I also can tell what g value I should use based on the units we're seeing in this problem. Since I'm seeing meters, that tells me that I should be using a g value of negative 9.8. Our projectile is fired from 2 meters above the ground. That's our h value. Initial velocity is 75 meters per second. That's v sub 0 at an angle of 35 degrees. That is our theta. So we've got all the information we need to set up the vector valued function that represents the path of this projectile. So for part A, we're going to use the projectile motion formula that says r of t is equal to v sub 0 cosine theta t for the I component, and then negative g over 2 t squared plus v sub 0 sine theta t plus h for our j component. And we'll just clean this up a little bit. I am going to go ahead and change these to decimals because 35 is not one of those nice values on our unit circle. When you do this, just make sure your calculator's in degree mode. So 75 times the cosine of 35 is about 61.4. So we've got 61.4 t for my I component. And then 9.8 divided by 2 is 4.9. So I've got negative 4.9 t squared. And then we need to know 75 times the sine of 35, and that's about 43. t plus 2 for our j component. So this is what we're looking for in part A when we're just asked to find the vector-valued function that represents the path of our projectile. In part B, we want to find the maximum height and the time which it occurs. So we're actually going to solve the time part first. So for part B, we want to know where y prime of t equals 0. We'll be at our maximum height when we've got that horizontal tangent line, or that horizontal tangent vector, and the tangent vector is the same as our derivative vector. But we only are concerned with the y equation because max height is only referring to what's happening vertically as our projectile flies through the air. So y of t is just the j component of our function. So y of t is negative 4.9t squared plus 43t plus 2, and we need the derivative for this. Y prime of t is going to be negative 9.8t plus 43, and we want to know where that equals 0. So just subtract your 43 over and divide your negative 9.8 over, which turns out to be about 4.39 seconds. When you read these problems, even though it asked us to find max height first, we always have to find, really have to find the time first. So now to actually figure out the max height, we plug this time back into our y function. So we need to calculate negative 4.9 times 4.39 squared plus 43 times 4.39 plus 2. And we will get a maximum height of about 96.3. And remember, the units we were using in this problem were meters. So this is 96.3 meters. That is the vertex of the parabola that we see when we graph the curve for this vector valued function. So the second thing we're often asked to calculate is range and flight time. And just like part B, we're going to have to solve flight time first. If we know the time in which the projectile hits the ground, we can then take that time and plug it into our x function, because x tells us what is happening horizontally. So first we need to figure out when we're going to hit the ground. And if we're hitting the ground, that means our height is 0. Now, you could solve this using the quadratic formula. You could graph this and see where it's hitting the x-axis. That's equivalent to where it equals 0. But no matter which way you solve this, you most likely can't solve this easily by hand, but quadratic formula definitely works. So if we figure out where this function equals 0, it actually equals 0 at 2 different times. We get times of approximately negative 0.046, and this is our x-intercept on the left-hand side of our parabola, and about 8.82 on the right-hand side of our parabola. So this negative value we just completely ignore, because for these application problems we consider time to start at 0, which means the negative value really doesn't make any sense in terms of the application for this problem. So our projectile, after being fired, will hit the ground in 8.82 seconds. So to figure out how far horizontally it has traveled in that time, we just need to plug 8.82 back into our x component function, which was 61.4 times t. So we're going to be calculating 61.4 times 8.82. And that will give us the range for our projectile, which is about 542 meters. So there's really not much else you could be asked to calculate for projectile motion. Really just being able to set up our vector valued function that represents the curve or the path of our projectile. And then the two values we're really interested in are the maximum height and the time at which it achieves it, and then the range and the time at which it is achieved. We're going to look at one more example. This one's quite a bit more difficult. It still involves projectile motion and our projectile motion vector valued function, but the solving part is quite a bit more difficult. And I just pulled this problem out of our textbook. It says a golfer stands 390 feet horizontally from the hole and 50 feet below the hole. Assuming the ball is hit with an initial velocity of 150 feet per second, at what angle or angles should it be hit to land in the hole? Assume that the path of the ball lies in a plane. So we don't need to worry about three-dimensional motion. It's just two-dimensional motion. So we've got some information about the starting spot and our desired ending spot. So I like to think of the starting spot as being 0, 0. And we want this ball, even though any of you play golf know this is completely unrealistic, we want the ball to land in the hole with no bouncing in between or no rolling in between. So yeah, it's kind of unrealistic, but that hole is 390 feet away horizontally and 40 feet away vertically. So we know initial conditions of 0, 0, and we know where we want this ball to go to as an x coordinate and a y coordinate. We're also given initial velocity, which is helpful. So we technically have initial velocity and initial height, which is 0. Because this problem is using feet for the unit, we're going to use g equals -32. And they're asking us to solve for the angle that will make all this work out perfectly. I'm going to set our x of t and y of t functions individually since we were not specifically asked to state the vector valued function. We know the x component for this vector valued function is initial velocity times cosine theta times t. And our y component function is, since we're in feet, it's going to be -16t squared plus v sub 0 sine theta t. And our initial height is 0, so you could say plus 0 if you want to, but we don't need it. And we do know our initial velocity is 150 feet per second. So we really have 150 cosine theta t and -16t squared plus 150 sine theta t for our two functions. We have a desired landing point for this ball. So since the hole is 390 feet away horizontally and 40 feet away vertically, we can set our x and y components equal to those values. We want these two things to happen simultaneously. In the time it takes the ball to travel horizontally 390 feet, we also want it to travel vertically 40 feet. So we come up with this system of equations. We've got 150 cosine theta t equals 390. We want our horizontal distance to be 390, and we've got -16t squared plus 150 sine theta t equals 40. And we need to solve this system of equations. There are two unknown values here, theta and t, and we're just being asked to solve for theta, which means I want to come up with a formula that has only thetas in it. So we're going to use substitution, and we're going to solve one of these equations for t, and then use it to replace the t in the second equation. And the first equation is a bit more simple, to solve for t. So I'm going to work with this one for my substitution. So if we solve this equation for t, we're going to have to divide over the 150 cosine theta. And we get that t is equal to 390 divided by 150 cosine theta. We can then use this t value to replace the t in our second equation. And then we'll have one equation that only has thetas in it. So I'm going to have negative 16 times that t value squared plus 150 sine theta times the t value equals 40. So it's still fairly complicated, but it now only contains one variable, so that's really helpful. So I'm going to do a whole bunch of simplifying. I'm going to calculate 390 divided by 150, and I'm going to square it, and I'm going to combine it with my negative 16. My cosine, which is squared, I'm going to pull up to the numerator as a secant squared. And I get negative 108.16 secant squared theta. And in my second term here, those 150s are going to cancel, and we've got a multiply by sine and a divide by cosine, and we can really put those together as a tangent. So that second term is 390 tan theta equals 40. When you're solving trig equations, if at all possible, we would like all of the trig functions to be the same. And it is possible to change secant squared into tangent. There's a Pythagorean identity that says secant squared is equal to tan squared plus 1. So I'm going to use that to make this equation quadratic in form. I'm replacing secant squared with tan squared plus 1, which is a Pythagorean identity. And that's going to help us because now we only have an equation that contains one variable, and this equation is now quadratic in form, which means we can solve it like a quadratic equation using a substitution. And anytime we solve a quadratic equation, we want it set equal to 0. So I'm really going to take that 40 that's on the right-hand side, I'm going to subtract it over to the left-hand side. And we've got, I distributed, and now I've got some like terms I can combine to clean this up a little bit. Got negative 108.16 tan squared plus 390 tan minus 148.16 equals 0. And all we have to do is a substitution for the tangent. Let u equal tangent, and that will make this look much more like a quadratic formula, or a quadratic equation, excuse me. So I've got a squared term, a linear term, a constant term equals 0. And then we can solve this pretty easily with our quadratic formula or using a graph. And we will get answers for u. And I'm just using my calculator to find these values. Anytime you have an equation equal to 0, you can, or an expression equal to 0, you can type that expression in for y equals in your calculator and look for the x-intercepts, because x-intercepts are the same as zeros. So when I do this, we're solving for u here because this equation's in terms of u. I get that u is about 0.432 and 3.17. But remember, u was the same as tangent. U was equal to tangent. So really, tangent is equal to these values. So to solve for theta, which is what we were asked to do in this problem, we just need to calculate tan inverse of these two values. And I'm doing this in degree mode in my calculator, and I'm getting about 23.4 degrees or 72.5 degrees. if we were to hit the ball at either of these angles, we could go exactly 490 feet horizontally. Was that correct? 490? Nope, 390, sorry. We could go 390 feet horizontally, and at the exact same time go 40 feet vertically. So when we look at the path of this projectile, we're starting here, and we want to get here. There's two ways that we could do that. We could do a really steep angle to get there, or we could do a really shallow angle. So either way we could get there.